As the holiday season approaches, many of us dream of a white Christmas, picturing cozy scenes of snow-dusted rooftops, twinkling lights, and laughter echoing through frosty air. The idea of waking up to a gentle snowfall feels magical, a perfect backdrop for festive celebrations and cherished family traditions. But sometimes, winter delivers a much harsher reality. Instead of a gentle dusting, we're hit with relentless blizzards, howling winds, and snowdrifts that bury cars and block roads, turning daily routines into daunting challenges. Imagine waking up to record-shattering cold that freezes pipes, disrupts power lines, and brings entire neighborhoods to a standstill. Suddenly, simple tasks like shoveling the driveway or getting to work become feats of endurance. This isn't just a movie scene, it's what happens when weather patterns high above our heads take a dramatic turn, sending shockwaves through the atmosphere and transforming our world overnight. Recently, both the US and UK have been rattled by sudden December cold snaps, leaving millions shivering, scrambling for extra layers, and wondering where the frigid air came from. These events can disrupt travel, close schools, and even threaten lives. The culprit? A phenomenon called sudden stratospheric warming, or SSW, a process that, despite its name, often triggers our coldest winters. It's a complex event that meteorologists track closely, as it can flip our weather from mild to extreme in a matter of days. This story begins in the stratosphere, a usually stable layer far above our heads, which can become a battleground in winter. Here, powerful forces clash, setting the stage for dramatic changes that ripple down to the surface. When that stability breaks, the consequences cascade down, unleashing bone-chilling Arctic air that sweeps across continents, dropping temperatures to dangerous lows and reshaping our winter experience. Let's pull back the curtain on the science behind these dramatic cold snaps, explore how SSW events unfold, and see what might be in store for the winter ahead. Understanding these forces can help us prepare for whatever the Arctic sends our way. Sudden stratospheric warming, or SSW, might sound like it should bring a welcome burst of warmth to the chilly winter months, but in reality, it's often the hidden trigger behind some of the most intense and memorable cold snaps we experience. This dramatic event unfolds high above our heads, between 6 and 30 miles up, in a layer of the atmosphere called the stratosphere. The stratosphere is best known as the home of the ozone layer, which shields us from harmful ultraviolet rays. During the long, dark polar winter, the stratosphere becomes extremely cold, creating a stable and frigid environment over the Arctic and Antarctic regions. But every so often, something extraordinary happens. The temperature in the stratosphere can suddenly spike by as much as 90 degrees Fahrenheit in just a few days, a rapid and dramatic warming that seems almost impossible. This sudden warming isn't caused by sunlight or any direct heat source from above. Instead, it's driven by powerful atmospheric waves, massive pulses of energy that surge upward from the lower atmosphere. These waves are often generated when strong winds flow over tall mountain ranges, or where there are sharp contrasts between land and sea, creating ripples that travel all the way up to the stratosphere. When these waves reach the stratosphere and break, they rapidly heat the air and disrupt the usual wind patterns, including the powerful polar vortex that circles the Arctic. The effects of this disruption start high above, but over the course of several weeks, the changes slowly work their way down through the atmosphere, eventually flipping our familiar weather patterns upside down and unleashing blasts of Arctic air that can plunge cities into deep freezes and spark major snowstorms. Sudden stratospheric warmings are natural events, occurring roughly every other year. Though their timing and intensity can vary widely, sometimes their impacts are barely noticeable, leading to only minor shifts in weather. Other times, they can dramatically reshape weather patterns for weeks, bringing prolonged cold, heavy snow, and even influencing weather far from the poles. Scientists and meteorologists are able to spot SSWs as they unfold, using advanced satellite data and atmospheric models to track the changes in real time. However, predicting exactly how these stratospheric events will affect weather on the ground remains one of the biggest challenges in meteorology. The atmosphere is a complex, interconnected system, and each SSW can behave differently. Every sudden stratospheric warming is like a new puzzle for forecasters, keeping them alert and constantly learning as they work to understand and predict the impacts of these powerful atmospheric events. The polar vortex isn't a storm, it's a vast, spinning pool of frigid air high above the Arctic. In winter, a strong vortex acts as a gatekeeper, locking cold air at the pole. But when an SSW strikes, it weakens or even splits the vortex, letting Arctic air spill south. The jet stream, normally straight, becomes wavy, allowing deep troughs of cold to plunge into North America, Europe, and Asia. Sometimes this leads to wild weather contrasts. Florida colder than Alaska, for example. The effects of an SSW take 1 to 3 weeks to reach the surface, giving meteorologists a crucial window to warn us. While we can't stop the cold, early warnings help communities prepare for deep freezes. Monitoring the stratosphere is now essential for anticipating major winter events. The polar vortex's fate is written miles above our heads. Sometimes, the key to winter's severity lies thousands of miles away in the tropics. The quasi-biennial oscillation, or QBO, is a regular wind reversal high above the equator, switching direction every 14 months. When the QBO is in its easterly phase, it weakens the polar vortex, making SSW and harsh winters more likely. A westerly QBO, on the other hand, strengthens the vortex and keeps Arctic air contained. Forecasters use the QBO's predictable cycle to gauge the odds of a volatile winter. It's a powerful, reliable signal. An easterly QBO means higher risk. A westerly QBO means more stability. This tropical wind pattern is a crucial piece of the winter weather puzzle. Even subtle shifts in the stratosphere can have icy consequences for millions. The Pacific Ocean's El Niño Southern Oscillation, or ENSO, is another major player in winter weather. El Niño years, with warmer Pacific waters, boost atmospheric waves that can disrupt the polar vortex and trigger SSWs, raising the odds of major cold outbreaks. La Niña years, with cooler waters, suppress those waves, keeping the vortex strong and Arctic air locked up. The interplay between ENSO and the QBO can either amplify or dampen the risk of a severe winter. Sometimes, their signals align. Other times, they conflict, making forecasts tricky. For the US, El Niño often means more volatility, while La Niña brings persistent patterns, colder in the north, warmer in the south. These oceanic shifts are global weather wildcards. Understanding them is key to anticipating what winter might bring. History shows just how powerful sudden stratospheric warmings, or SSWs, can be. These rare atmospheric events have the potential to disrupt weather patterns on a massive scale, sending shockwaves through the climate system and impacting millions of lives. In December 1989, a major SSW shattered the polar vortex, that swirling mass of cold air high above the Arctic. This disruption unleashed a torrent of Arctic air, plunging deep into the United States and catching many off guard with its ferocity. Record lows swept across the country. Kansas plummeted to a bone-chilling -20 degrees, while Florida's iconic citrus industry suffered catastrophic losses as groves froze solid. The freeze destroyed crops, threatened livelihoods, and left a lasting mark on the region's economy. The power grid strained under unprecedented demand for heat, with utilities pushed to their limits. Cities from the Midwest to the South set all-time cold records, and daily life ground to a halt as people struggled to stay warm and safe. More recently, the beast from the east in 2018 brought heavy snow and chaos to the UK, while Texas's 2021 deep freeze left millions without power. Both events were preceded by SSWs that destabilized the polar vortex, showing that these phenomena are not just historical curiosities, they remain a real and present threat. Each of these extreme events provides scientists with valuable data, helping them refine their models and deepen their understanding of how disruptions high in the stratosphere can trigger chaos at ground level. The more we learn, the better we can prepare. The lesson is clear. What happens 20 miles above our heads can have life-altering impacts below, affecting everything from agriculture and infrastructure to daily routines and public safety. These case studies are vital for improving forecasts and preparedness, giving emergency managers and meteorologists the tools they need to warn communities and save lives before the next deep freeze strikes. The mechanism is always the same: a stratospheric disturbance, a polar vortex breakdown, and a cascade of extreme cold that sweeps across continents, reminding us of nature's power. History urges us to respect the power of the upper atmosphere and to never underestimate the far-reaching consequences of events that begin far above but end up shaping life here on the ground. So, what's in store for the upcoming winter? Early indicators point to a westerly QBO and developing La Niña, both favoring a strong, stable polar vortex. This combination lowers the odds of a major SSW and widespread record-shattering cold snaps. But that doesn't mean a mild winter everywhere. Regional cold and snow are still possible. Long-range forecasts are about probabilities, not certainties. The atmosphere is full of surprises. Other unpredictable factors can still tip the balance as winter unfolds. For now, the outlook suggests a lower risk of a polar vortex breakdown, but vigilance is key. Winter is a marathon, and the final story is always written in real time. We'll keep watching as the season evolves. Predicting winter months in advance is one of meteorology's toughest challenges. Tools like the QBO and ENSO stack the odds, but can't reveal every twist. The timing and intensity of cold snaps can only be forecast with confidence a week or two ahead. The atmosphere's chaotic nature, tiny changes growing into big impacts, means surprises are inevitable. For industries and the public, probabilistic forecasts are still valuable for planning. Scientists are improving models and using AI to find new patterns. But uncertainty will always be part of the forecast. We can see the big picture, but the details only emerge as winter arrives. While we can't predict SSWs months ahead, we're now excellent at spotting them as they begin. Agencies like NOAA and the Met Office monitor the stratosphere with satellites and weather balloons, providing a critical early warning system. When a rapid warming is detected, scientists track its evolution and run models to predict surface impacts. This gives us 1 to 2 weeks' notice, enough time for emergency managers, utilities, and the public to prepare. Early warnings save lives and property, turning scientific vigilance into real-world readiness. Our relationship with winter is a dance between prediction and preparation. The study of SSWs has revolutionized our understanding of winter's risks. As the cold season approaches, we can take comfort knowing experts are watching the skies for us.